Okay, so this time we'll be talking about learning from and for knowledge bases. So basically this is talking about how neural networks can either be used to extract knowledge from text or how knowledge that has been extracted can be used to inform neural networks and the representations therefore. So the first thing is talking about knowledge bases in general. I think this was covered a bit in the reading, but they're basically structured databases of knowledge, usually containing, for example, entities and relations, which are edges between nodes. This is the most canonical form of a knowledge base, but there are also lots and lots of other kinds. So basically any database or whatever that you can think of can be considered a knowledge base, and you can think of ways to encode them. But because I want to cover the kind of most standard ways of doing things, I'm going to mainly cover ones that take into account these things. So I'm going to talk about, as I said, how to learn and create or expand knowledge bases with neural networks, and how to use the information in knowledge bases to improve neural representations. What I'm not going to cover this class, because we've already kind of covered it, is how we can use this knowledge to better answer questions. I'm going to cover it a little bit here maybe, but we also talked about this in the semantic parsing class. So in semantic parsing, you can go basically from language to a database query or some other structured query that functions on these knowledge bases. So I'm not going to cover that quite as much in this class as was covered the previous time. So knowledge bases have been around for a long time. So WordNet is one example that I cited at the very beginning of this class. So WordNet essentially is a large database of words, including parts of speech, semantic relations, like is, etc. And at about the same time, or maybe even before that, there was a database called Psych. Do people know about this or have heard about this to some extent? Oh, not that many people actually. Okay, this is a famous project, and it's a controversial project. It's basically a manually curated database that was attempting to encode all of common sense knowledge. It was created manually over a course of 30 years by first people in academia, and then people then kind of spun off as a company. And it has all kinds of things like things at the top, and then intangible things, individuals, etc. You go all the way down, and you have domain-specific knowledge, you have domain-specific facts and data, etc. So the reason why this is a famous project is it was actually pretty large scale and very inspiring. It's also controversial because, for example, Pedro Domingos, who's a very controversial guy himself, said this is the biggest failure in the history of artificial intelligence, which I don't necessarily agree with. It was useful for some things, but the reason why he was saying this is because it's so difficult to encode all of our common sense knowledge by hand because there's so much of it and there are so many exceptions that it's really hard to do. And this kind of you obviously can't live up to the promise of encoding all common sense knowledge because there's too much of it. So he was saying it failed at that aspect. More recently, there are counter-arguments to the fact that you can't encode all of knowledge. And one example of this is DBpedia. So DBpedia is extraction of structured data from Wikipedia info boxes, like the ones about Carnegie Mellon University here, for example. This is also manually curated knowledge. This is where humans go in and curate knowledge on Wikipedia, but importantly, they're not doing this necessarily for machines. They're doing it for humans because it's convenient for humans to come look at this. They're also doing it on a much larger scale with hundreds of thousands of editors as opposed to just a few people working there. So there's other big projects like BabelNet. So BabelNet basically, sorry, I skipped the Yago slide. Yago's like another thing that focuses on temporal information. But basically it incorporates various sources of information like WordNet and Wikipedia, tries to cross-link them, and also importantly tries to cross-link them across languages. So it's a multilingual database as well. And then the kind of big thing that lots and lots of people have been using recently is Freebase, which has also been called Wikidata, has been renamed into Wikidata. And basically, it's a curated database of entities, from these sources like Wikipedia, and also just annotated, extremely large scale. So this is an example. You can actually go to the Wikidata site and look up particular entities. You can see all the information they have about the entities, and you can also suggest additions to this if you want to. So this is what people have been using a lot because it's very, it's well curated, and it's also very, very large scale. Okay. So this is just a background of like what kind of things are out there. Whoops. But there's a big problem of knowledge base incompleteness, where even at extremely large scale, knowledge bases are by nature incomplete. And for example, West et al. 2014 found that Freebase, the largest database of its type, 71% of humans had never been born. So this seems wrong, right? So essentially, no matter how big you make it, you're always going to be missing humans because you can't. It'd be pretty difficult to come up with a record of all humans who ever lived, and the more humans you add, the more likely you're not going to be able to know their name, their dates of birth. So essentially, it's this chicken and egg game where you add more entities and then you're missing relations with them. You add more relations and you need more entities, etc. So then the question is, how can we extract information for the knowledge bases? And there were lots of examples of this shown in the reading. And most of these focused on how you could extract these directly from text. So you have a textual mention of particular relations and you want to extract them. These are very, very nice methods that focus on individual textual snippets. But actually, with neural networks and embeddings, there's been a lot of work on focusing on embeddings as kind of a global view of words or entities and the relations between them, and using this to perform relation extraction. So as I noted before, as Mikloff et al. Noted, we have man goes to woman, uncle goes to aunt, king goes to queen. So this is precisely a relation, right? This is a relation between the word, specifically a gender relation between these nouns. And actually, when people say semantics, I feel like semantics is a very overloaded term right now. So basically, if you take anything and turn it into a vector, people start calling it semantics. But semantics actually has a definition in linguistics, and one of the definitions of lexical semantics, if you look it up in a linguistics textbook or the proxy for a linguistics textbook, which is Wikipedia, it says it's the study of the meaning of words and the relationships between them. So precisely encoding these relationships is a fundamental part of the definition of lexical semantics. So there's lots of different ways to do this. And basically, what you want to do to extract relations is to take words and decide whether king and queen have a particular relation that holds between them, or whether Carnegie Mellon University in Pittsburgh, Pennsylvania has a particular relation that holds between them. And one example of this, one kind of early example of this is relation extraction with neural tensor networks. And the idea here is that you have essentially a set of relations that already exist in Freebase or some other curated data set that you want. And you just feed two embeddings from the words to a multi-layer perceptron that predicts whether a relation exists. So the idea here is basically you have embedding 1 and embedding 2, where embedding 1 is kind of the subject of the relation. Embedding 2 is the object of the relation. And these are two matrices. You feed them through a function, also multiply this by a vector, and get your score for that particular relation. The neural tensor network that they propose in this model basically adds bilinear feature combinations in addition. So this thing over here is kind of the standard way of doing it with a multi-layer perceptron, but you can also add bilinear feature combinations between them. You can add a bias about whether the relation exists or not, and then you similarly feed this through a network, and you get the answer. So this is a powerful model, and it works very well for high frequency relations. But actually, you have a lot of parameters in this model. For each relation, you have a matrix. So you have the number of parameters is equal to the size of the embedding times the size of the embedding times the number of relations. So that's a lot of parameters to be learning how to do something like this. And it's especially a lot of parameters for relations that you haven't witnessed very commonly. And because Freebase has so many relations, it's very common for you to not have much training data for this. So there's also another method that came out at about the same time that is super, super simple. And basically, all it does is it says, hey, Mikolov had a good idea. You just follow a vector in space, and you get something that looks kind of like it should follow that relation. So what you do is you try to learn a single vector that you can shift the embeddings for each relation. And then you train this using a margin-based loss to try to ensure that those pairs that actually exist in a relation actually get a higher score than those that do not. So simply, you have the size of the margin here, and then you have the distance between the head plus the shift vector and the tail, and then the head of a negative example plus the shift vector plus a tail. So it's a simple margin-based loss to try to predict whether this relation exists. This is intentionally simpler than the neural tensor network. Yeah, sorry, go ahead.
What's the shift vector here?
So the shift vector, this is just another vector that's the same size of the embeddings. So to give the example from the Mikolov thing, it would be this blue vector here. Whereas entity 1 would be the vector for uncle, and entity 2 would be the vector for aunt.
So you're getting this symmetric verse and calculating the shift by subtracting these two vectors?
Yep. You just calculate the shift by adding the two vectors. So it's like an extremely simple model, but it actually works pretty well. It works maybe as well as the neural tensor network model. Are there any other questions about this? Okay. This model up here was called trans-E. They gave the name trans-E for translate embeddings, translate in embedding space. So this is a very simple and attractive model, but it has a few obvious shortcomings, and there's a few methods that people used to fix these as well. So basically, the idea behind this is that it's not realistic to assume that all dimensions are relevant to a particular particular relation. And actually, a very obvious example of this is, the reason why it's not necessarily a good idea to call word embeddings a semantic embedding is because there's actually lots of other things that could be included in the word embedding. So for example, frequency information. The frequency of the word might be encoded in the embedding, which has very little to do with semantics, right? The part of speech, doesn't have to do with meaning necessarily. It has to do more with syntax. So there's lots of other dimensions, and many of these dimensions may not be relevant to a particular relation. So what you would like to do is you would like to project, or what they do in this paper is they project word vectors onto a hyperplane specifically for that relation, and then they verify that relation. So what this allows you to do is, for example, remove all of the information about the irrelevant aspects of the word vector, and keep all the information that's important for keep all of the information that's important for determining whether the relation exists, and then do a simple thing. So basically, the idea here is if you look at the trans-E model, if you have H and T and R be the relation, then you need to do this. Then this is what it looks like. But in the trans-H model, which is their proposed model here, you basically project these onto a hyperplane and then verify the relation within that hyperplane. So the way this looks is pretty simple. You have a vector for the relation that basically projects this each one onto this hyperplane, and then you also add the direction for the relation. There's also another expansion that uses a full matrix instead of a vector for each. Probably how well each one works depends on the amount of data that you have, but this is another option here. This is particularly good for things like one-to-many relations. So like, for example, let's say you want to find all of the people who graduated from Carnegie Mellon. You want to find the graduated from relation between Carnegie Mellon and people. And there's lots of people who graduated from Carnegie Mellon in Wikipedia, for example. What you would want to do is you would want to project away the dimensions that tell you exactly what their occupation was, but just keep the dimensions that told you where they were educated. So this is something that could do that as well.
From this algebra one here, we're assuming that the same, just a single vector for each relation for the V vector.
Yes. So you have a single vector and you have a single W here. Well, you have two, sorry. You have the D vector and you have the W vector. So this is kind of the projection vector. This is the direction.
Too restricted an assumption. So let's say that every relation, once you fix the relation, it's kind of like saying the shift is got to be this particular amount.
Once you fix the relation, you say the shift is going to be the particular amount. I mean, so it is making a very strong assumption about the embedding space. So it's making the assumption that the embedding space is kind of linearly coherent, and it's making an assumption that the embedding space is linearly coherent and encodes this relation in a linear way. And if that's not the case, then maybe you need to use a neural tensor network that is more highly parameterized, for example. Okay, these are good questions. Any other ones here? Okay. So there's also a nice model by Chija here, and he basically the model is a decomposable relation model, and the idea being that there are many relations, but many of the relations are very similar, and can be represented by a limited number of kind of underlying basis relations, which they call concepts. So the method is you treat each relation map as a mixture of concepts with a sparse mixture vector alpha. So another way you can think of this is basically for each relation, you're doing attention over these like latent concepts and composing the relation vector from these latent concepts. And this is good because this allows you to have less parameterization of the model, or fewer parameters for the model, which allows it to generalize better, especially to kind of rare relations. But also you can, this allows you to essentially like visualize the similarity between relations as well. So one existence of this is similar to, for the tail and the head, this is a symmetric relation. Similar to is a symmetric relation, so the tail is the same as the head. Whereas hypernym is not a symmetric relation, right? So a hypernym points in one direction where the tail of the hypernym, let's see, the tail of the hypernym relation is a child of the concept for the head of the hypernym relation. And vice versa, hyponym is the tail of the hyponym relation is a parent of the head of the hyponym relation. And you can see that it actually finds that despite the fact that there are these four types, it kind of neatly finds that the head of the hyponym relation is the same as the tail of the hypernym relation, etc. So I think this is a kind of interesting model. If you're interested in relation extraction, you can take a look at it as well. Okay, so this was all about learning from embeddings. Are there any questions about this? Actually, I just realized as I was talking about this, I forgot one kind of important thing. So the important thing that I forgot to say is actually in knowledge bases, it's very common that you're not using word embeddings, but you're rather using, it's very common that you're not interested in relationships between words, but you're interested in relationships between entities, right? So like Carnegie Mellon University, and Carnegie Mellon University is 3 words. So in order to do this for knowledge bases that are over entities, you essentially need to have embeddings of entities. So the question is, how do you do this? There's a super simple method, which I can cite the paper here. So this is the name of the paper, Jointly Learning of Embedding of Words in Entities for Named Entity Disambiguation. And basically what they do is they take a big text, they identify all of the entities in the text, and then they just train a single embedding for the entity like it was a single word. And the easiest way to do this is to take Wikipedia. And in Wikipedia, you have text where there are anchor tags between Wikipedia pages, right? So if you go to the Wikipedia page for Carnegie Mellon University, I'm sure you would find an anchor text for Andrew Carnegie, and the Andrew Carnegie link would point to Andrew Carnegie. So you just take the identity of the page that link links to, and you use that as the identity of the entity that you then embed in the text when you go and run Word2Vec. So by doing this, you take all of Wikipedia. Wikipedia has all of these links. You just run Word2Vec over it after converting all of the anchor tags into their corresponding entities, and you get entity embeddings. So there's better ways for doing this, but this way works pretty well, and it's super easy. So and there are pre-trained embeddings for many of the entities on Wikipedia that you can just download. Okay. So next, I'm going to talk about learning relations from text. This was a topic from the reading, so I'm going to kind of breeze over the parts that were actually in the reading and get to the neural parts. So kind of like one of the state-of-the-art models, as was noted in the reading for this, or state-of-the-art, I guess, methods or learning paradigms, is distance supervision, where basically given an entity relation entity triple, you extract all the text that matches this and use it to train a supervised system. So the idea being that you find Steven Spielberg and Saving Private Ryan, and you have the director relation between Steven Spielberg and Saving Private Ryan. And you can see that you can extract text that basically indicates the director relation. Some of the things are more direct, so like Saving Private Ryan, directed by Steven Spielberg. Some of the things are less direct, like Steven Spielberg's film Saving Private Ryan, which could also indicate the writer relation or the producer relation or even the actor relation or something like this. So this is a noisy form of training data. So there's a fair amount of work on doing basically training models for this. I'm going to skip all the feature-based work that was written in the reading and move directly to neural models. And basically, this model here is relation classification with recursive neural networks. And what they do is they create a syntax tree, do tree structured encoding of the syntax tree, and classify the relation using a representation of the minimal constituent containing both of the words. So what this looks like, essentially, is okay, this is not a very good example. They did other things in this paper as well, but like it would be, for example, Saving Private Ryan, directed by Steven Spielberg, is a constituent. So that you would extract this constituent, do syntactic encoding of this constituent, and you would get the result. They specifically had something called a recursive matrix vector model. This is not really important. You can just think of it as another way of encoding tree structures, like all the other ones I talked about a few classes ago. Another method, which also works and is perhaps a little bit simpler, is using CNNs. And basically, they extract the features without using any syntax using CNNs, including lexical features of the words themselves, and lexical features of the whole span between the words extracted using convolution. So the idea being you have word representations for all of these, you extract the features, and you feed them through an output where the features that you extract are extracted using a convolution or something else. So I think you get the general idea. You know, if you're interested in doing this, you can take a look at the paper for details. So these are kind of, you know, straightforward things that more or less follow the things that we've done before for text classification or whatever else. I think the more interesting thing starts happening when you start thinking about things that are specifically informed by the fact that we're trying to model relations between words. So one example of this that was a little bit maybe more creative was modeling textual links between words with neural nets, aggregating over multiple instances of links in dependency trees. So the basic idea here is that they come up with subject, founder of, object as an example of a minimal dependency path between the subject and the object of the relation. And then they take the relations and model these relations using a CNN. So they feed this into, they feed this relation path into the CNN itself. So this is, the modeling part is simple. Basically, you have a CNN where each word and each connection between the words is essentially a token in your input. And then based on this, they can do max pooling over this, and then use this for relation classification itself. So I think this is really nice. One reason why this is a nice thing to do is actually it helps, if your dependency parser works well, it helps boil down to really the most important things that you can have to decide whether it's a relation or not. And it does so in an efficient way. CNNs are efficient extracting these paths. If you did it in Python, it might be a little bit sluggish, but if you did it in C++, for example, you could do this over a huge amount of data relatively efficiently, et cetera. So another thing that kind of tackles a unique problem with respect to relation extraction, but still could be very, very useful in other types of problems, is modeling the noise that you get through distance supervision. And basically, the idea here is that distance supervision is a way of creating noisy training data, right? It's noisy supervised training data. So how do you account for this fact? And so the way they chose to do this is by modeling this noise directly. And I think this is a really clever model that you could use in other things, as I just said before. So like, let's say you're doing text classification and you know one of your data sets is really high quality, but another one of your data sets is not high quality. You got it from Mechanical Turk, where you paid the Turkers like 5 cents per labeled example or something, which I don't think you should do. You should pay your Turkers well. But let's say for whatever reason, whoever created this data set did this. Then you know they're not very motivated, and they're not as motivated as the CMU graduate student who labeled some other small set of data. So you have a noisily labeled data set, and you have a cleanly labeled data set. So what they do is they have an encoder, they have embeddings, then they make a prediction from this encoder, but then they also have a noise model, where the noise model predicts kind of a transition matrix between the predictions. So then what you do is you take this transition matrix and you multiply it by the probability distribution, the predicted probability distribution. So let's say P tilde is your predicted one, and N is your noise matrix. Your final prediction is then P equals, I totally did not intend that, but I just solved a major problem in computer science and should get $1 million. But okay, let's ignore that and assume that this is probability and this is a okay. So basically, this is what you do. This is your noise matrix, and then your final observed distribution is what you use to actually train your model. So by controlling the transition matrix, you can adjust to the amount of noise that you expect in the data. And what they did was they did a trace normalization, which basically tries to make the matrix close to the identity matrix. And the reason why is you don't want your predictions to just become completely decorrelated with, you know, like what you what you're optimizing over. So you want this. If this is the identity, obviously your final predictions will be equal to whatever you get out of your model. So they try to make the matrix close to the identity so you don't diverge too much. And they also start training with no transition matrix on data expected to be clean, like the one that you labeled yourself and you trust, before phasing in training on the full data, where they actually do use this transition matrix. So I think this is a pretty clever method that goes far beyond, you know, like anything that you have here. Sorry, far beyond the application that you have here. Okay. Any questions about this? Yeah.
Yeah. Like they're using recurrence, traditional internet to. I wonder, like, on the bottom level, we have embedding for each words and each relations, but they follow some like algebra relations, like individual something or.
I couldn't hear that.
So it's like we have embedding for word, also for a word here. So we have embedding for relations, but they follow some like trans-U or trans-H relations.
So these relations here, sorry, I'm not sure if I was completely clear. These are syntactic relations according to a dependency tree. So these are not the relations we actually want to model. What we want to model is like founder, for example.
Yeah, I know, but I wonder like whether this whether we could evaluate the embedding of these relations by further prove that the effective model.
Evaluate whether you did a good job of embedding this relation by how effective the model is. I think that's definitely an indirect measure of how good the embeddings of the relations are. Yeah, so.
But that is not necessary, right? Or
Well, yeah, I guess you're not really, like this particular paper didn't really try to evaluate whether the dependency relation embeddings were good or not. I think it'd be an interesting thing, to think about. I don't know necessarily in the context of this model, but maybe in the context of other models. But yeah, they definitely didn't evaluate these on their own. Yeah. Okay, any other questions? Okay, so also I'm going to talk about schema-free extraction, which was also called open information extraction. And the reason why I called it schema-free extraction is because up until now, all of the databases that I talked about had something called a schema, which basically delineates what kind of relations you cover. And even Freebase, which is extremely large, has a list of all of the relations you care about, like date of birth, person, there were better examples in the reading, but like person, nationality, or something like that. So what schema-free extraction does, open information extraction, as was also written in the reading, the text is the relation here. So if you have United has a hub in Chicago, you have United has a hub in, and Chicago is the headquarters of, etc. So this itself is kind of the relation that you're trying to extract. So this is great because you can extract anything. You can extract any relation that's mentioned in the text. But it's not so great because you can't easily abstract over like different types of relations being basically implying the same thing. So like to give an obvious example of this, founder of would be a different relation than co-founded, which would be a different relation between co-founder of, despite the fact that these are very similar relations, obviously. Rule-based OpenIE, there's things like text runner and reverb. The basic idea, use a parser to extract according to rules. For example, the relation must contain a predicate, must be subject-object, subject and object must be noun phrases, etc. Optionally, you can then go in and train a fast model that's quick to run over the entire web. Or maybe one that's robust and doesn't require a good parser because the web, it's hard to parse the web well. And then also, you can aggregate multiple pieces of evidence heuristically to find common and reliable extraction. So if you've seen that, like Steve Jobs was the co-founder of Apple many, many times, then you would assume that that's reliable, whereas if you haven't seen it many times, you would assume it's not reliable. So how do you do this in neural models? There's actually not been a huge amount of work on this. And I think one of the reasons why there hasn't been a huge amount of work on this is large-scale data sets are sparse and evaluation is difficult. So this was also mentioned in the reading as well, I think, but largely these models were evaluated by just extracting a bunch of extractions using rule-based methods and then having a human evaluate them to see whether they actually made sense. But unfortunately, the heuristics are not perfect, and they described error rates of anywhere between 12 to 18%, even among the most popular and reliable relations. But recently, there's been a little bit of work to create large data sets for relations or for semantic role labeling by asking simple questions to crowd workers. So this is a kind of nice paradigm where basically the idea is you take UCD finished the 2006 championship as Dublin champions by beating St. Vincent's in the final. And then you have a whole bunch of questions that you then ask crowd workers and ask them to, answer these. And so one question is who finished something? What does this tell you about the answer to this question? Any ideas? Maybe it's not a relation. It's maybe more of a relation with the verb. What grammatical function does the UCD have in this sentence? Subject, yeah, exactly. So then what did someone finish? This is the direct object. What did someone finish something as? I actually don't know what this. I don't know what the function of this is. What is this? Is this the? Anyone familiar with semantic role labeling? People are saying things, but very quietly. I actually don't know. So this is the means or the method, for example, the third one. Then who beat someone? So this is the subject again. When did someone beat someone? This is the time. And this is who did someone beat? This is the direct object. So basically, by asking these questions, you don't actually have to know what the direct object is or stuff like this. And you can come up with a short annotation manual that even crowd workers can read. So by doing this, they created a big data set for semantic role labeling. And it turns out that semantic role labeling, which is basically who did what to whom, you can take the data and do some deterministic transforms into it to convert it into something that looks pretty close to what you want to be extracting for open information extraction. And the modeling part actually isn't very consequential at all. It's just a ByLSTM beginning in and out tagger, where you convert this into the subject, begin subject, predicate, begin direct object, indirect object, indirect object, and sorry, I don't know the semantic role, and then like method or means, begin method or means, and then in method or means all the way to the end. So basically, what you can do is once you have a large data set like this, you can turn it into a tagging task and train a supervised neural tagger on this data. And this is pretty interesting. It's nice because it turns information extraction into something, open information extraction into something that looks very much like a supervised method, which is easier to do. Okay, so as I said, there's not a whole bunch of neural methods for doing open information extraction. So this is something, might be interesting to study. Okay, so now the next thing I want to cover is learning relations from relations. So what I mean by this is essentially we know that knowledge bases are incomplete, but they're still very big and they still have lots of information in them. So can we use the knowledge that we do have in knowledge bases to model things? So word embeddings essentially, if we think about what they give information of the word in the context. This is indicative of KB traits, but other relations or combinations thereof are also indicative. And this is essentially, it's a link prediction problem in graphs. So we had an excellent talk about graph neural networks in the LTI colloquium last week by Yuri Leskavec. But this is exactly the link prediction problem that he was talking about. And there's a bunch of different ways to do this. And I'm just going to go through a few of them. There's actually many, many more other than the ones I'm going to cover here. But these should give some good references. So kind of stereotypical, a stereotypical thing, and also something that Ilya Sutskever did before he created the sequence models we all know and love now, was knowledge base completion. And basically the idea is we can model relations by decomposing a tensor containing entity relation entity tuples. So the idea is super, super simple. We just make a huge tensor where the tensor is subject relation object, where we have a 1 if that relation exists, 0 if that relation doesn't exist. It's a huge tensor, obviously, because it's over our whole knowledge base, but it's also very, very sparse. So then you do a sparse tensor decomposition and reconstruct the tensor, and anything that has gone from 0 to a value close to 1 is something, due to our low rank approximation, is something that you should maybe consider being a part of the knowledge base. This is also very similar to collaborative filtering, if people are familiar with this from recommender systems. So, this is how Netflix recommends you your next movie to be watching, where instead of decomposing over tensors, they're decomposing over like genre, and what other movies you've seen before. So this is a powerful method that can be used for a lot of things, but one particularly interesting one is you can actually use this to reconcile schema-based and open information extraction. So when we have a knowledge base, which may be very incomplete, or it might not have all the relations that we're interested in, but we have text from OpenIE extractions, which is also good, but we might not necessarily know how they correspond to things in the knowledge base. We can use something called a universal schema, which essentially embed relations from multiple schema into the same space. So this is a really elegant method, or I don't know about elegant, but basically like it's really simple, but it makes a lot of sense, which is that you just take all of the relations from your OpenIE system, which are actual text, like professor at and historian at. Then you have the employee thing in the freebase knowledge base. And then you have the member thing in the TAC knowledge base. So these are all different relations that we have evidence of. You just put them into one big matrix, and then you do matrix factorization. And once you've done matrix factorization, once you have historian at university, you'll find that this very highly entails this relation, which you didn't have in your original knowledge base, et cetera. So I think this is really nice. It allows you to reconcile completely disparate knowledge bases. It allows you to reconcile textual knowledge bases with other knowledge bases, et cetera. Another thing it might allow you to do is reconcile things that are in OpenIE extractions but aren't in your knowledge bases, which would allow you to think about maybe, hey, there's a relation that isn't covered well by our knowledge base, and maybe we should be expanding our knowledge base. So, yeah. Are there any questions about this? Yeah. The y-axis is, let me see. It's two entities. It's an entity tuple, so it's the subject and the object. So it's their methods actually. Sorry, I should have mentioned this. So it's an entity tuple, so it's a subject and an object of a relation, and then you're just trying to fill in whether the relation exists or not. Their method's actually a little bit more tricky than this. It's not just a matrix factorization. It's also adding additional features where you just look at the relation between Ferguson and this, Ferguson and this, Harvard and this, Harvard and this. So it splits the tuples into single, like subject, single object, and it also does some other stuff like embedding things into low-dimensional embeddings and stuff. So you can take a look at the paper for more details. Any other things? Okay. So another interesting thing that's kind of unique to relation extraction or knowledge bases is that you can model paths over relations. So multi-step paths can also be very informative for indicating individual relations. So there's a paper from William Cohen's group here at CMU, back when he was at CMU. And given a word, recommend a venue in which to publish the paper. So the idea here is this is really this is a really nice thing to have, because like let's say you've just written a paper and you don't know where to submit it. It can tell you where you should be submitting your paper. I don't know if it will tell you where your paper will be accepted, but it might at least tell you where to submit it. And the idea is basically you can create relations like the paper's title has the word, and the paper was in a journal. And then you take this relation path, and you basically learn a weight over the relation path and how predictive it is of the journal that it should be published in. Then you have another relation path, which is the word is in the title of the paper, and the first author of the paper first authored another paper which was in that journal. Or the word is in the title of the paper, and any author of the paper, any author had another paper that was in that journal, etc. So basically, these are discrete. These are features that you can extract, and then you can train a model that tells you what paths are maximally predictive of that path existing, other than the path itself, obviously. So this is an interesting method, and there's an interesting kind of way of using this to train embeddings of entities and embeddings of relations. And basically the idea is that if you have a embedding-based relation prediction model, such as trans E or trans H or something like this, the problem is if you actually take multiple steps in the space, this can result in error propagating. So let's say you're a little bit off of the entity that you want to have in your first step in a path, and then you're a little bit more off in a second step in a path. You might end up being completely wrong about your inference. So let's say you had a question that you want to answer by traveling through embedding space. So it's like, where did Tad Lincoln's parents live? Is the question, or something like that. So Tad Lincoln was Abraham Lincoln's son, and so if you travel up the parent relation, and then you additionally follow the location relation, if you kind of mess up the parent relation and instead get not Abraham Lincoln, but like some other Lincoln or something like that, then you'll mess up even worse when you try to find the location. So the idea of this method is basically, instead of just optimizing embeddings, you're additionally optimizing whether you get the answer after 2 steps through the embedding space correct, or after 3 steps through the embedding space correct. And interestingly, they show that not only does this help inference that requires multiple steps, it also helps inference that requires only a single step. And I think the reason why is because if you have a big knowledge base like Freebase, the number of single step relations that you have in the knowledge base is large, but it's still limited. But the number of 2-step relations you have is really huge, right? You fan out quadratically in the number of relations you have. So this also allows you to augment your training data that you use for training something like this. Okay, are there any questions about this? Okay. So there's another interesting paper also by William Cohen on this, on differentiable logic rules. And basically the idea is it's a way to consider whole relation paths in a differentiable framework. So the idea is that you have has office in city and city in country, and you want to predict whether the has office in country relation is correct or not. And the way this works is basically you treat the path as a sequence of matrix multiplies where the rule weight is alpha. So the way this works is you take matrix multiplies through this path where each matrix multiply is weighted by the strength of this this method here. Or sorry, each path is weighted by the strength of this method here, and then you weight over all of the paths. So basically the way you can think of this is it's a combination between this method, which gives you weights over each of the paths, like how likely the path is to entail a particular relation, and this method that's optimizing over the paths themselves. So it's a way that you can get both worlds, like the best of both worlds. So I think this is a nice paper. You can take a look if you're interested more. Okay. Are there any questions about this? Okay. So the last thing I'm going to talk about is using knowledge bases to inform embeddings. And basically the idea is, can we take a knowledge base and can we use this knowledge base to improve the accuracy of our neural model itself? So I think this is an interesting thing to think about. Is there anybody, so can anybody think of a reason why, like a theoretical reason why we might need to have a knowledge base in order to answer questions, despite the fact that we have our BERT multitask DNN super squad model that gets human level performance on squad or something like this. I think there's maybe a kind of clear theoretical reason why you would still want a knowledge base if you were Google or something like that and you wanted to answer a bunch of open domain web queries. Any ideas? Yeah.
I think it's fundamentally a search operation, so a simple lookup operation. So a database is the easiest or simplest way to do that.
Okay, it's fundamentally a search operation or a lookup operation. So a database is the best way to do that. Can you be a slight bit more specific about best?
Because maybe if we know the ground truth, we can just pick up and show the ground truth.
Yeah. If we know the ground truth, we can just pick up and show it. Yeah. So I think there's 3 arguments here actually. So that's the answer I wanted, but I'll be a little bit more precise. Oh, did you have a?
Is it because even for this identical word, we may have different semantic meanings that we may need extra information from knowledge base? A good example would be say we will have we need some information about homes, but we need extra information about whether this is a movie of homes or a novel of homes or something because a single word could have a lot of roles or concepts, so we need extra information to form the embedding of.
So these are 2 different things. Just to repeat the comment, a single word might have multiple meanings, and because of this, you would need a knowledge base to tell you about which of those multiple meanings might exist. I definitely agree with this, although you could make an argument that something like contextualized word embeddings like BERT would pick this up already. But it is a good point because I don't think you necessarily know this. But to get back to the one here, I definitely agree that this is a search operation. So number one, if you can look something up in a database, you're certain to get the answer correct. So like if you do a SQL query, you're never gonna fail. Like at the SQL query, it's a deterministic operation, whereas things like embeddings, it's very likely that you'll get it correct, but it's also you're not necessarily going to be able to get this for sure. I think a bigger, a pretty obvious argument is that Freebase is a lot bigger than BERT. Like Freebase is multiple, I don't think it's terabytes, but it's at least multiple gigabytes of data stored in an extremely efficient format of integer ID, integer relation, integer, ID basically. So just the fact is that Freebase has more information than even our largest neural models will ever have. And I don't think it's reasonable to assume that BERT will encode all of the knowledge in Freebase, even if all of the knowledge in Freebase exists on the web, just because it doesn't have the capacity to do so. assuming it did have the capacity to do so, then still you would have to have text that tells you about all of these relations. And I think it's arguable that text about all of the relations in Freebase exists. And it's actually also arguable that you could learn it from a single example somewhere on the web, the way you can for a non-parametric model like Freebase. So another way to think about this is BERT is a parametric model. It has a fixed number of parameters and you optimize them over a large text space, whereas Freebase is non-parametric. It expands as people add more relations, it gets bigger and bigger and bigger. Well, not Freebase actually, because Freebase has been deprecated, but DBP, Wikidata. So when you get to the very, very long tail of facts or the very, very long tail of, even translations or something like that, the parametric models like fully neural models tend to suffer about this. And also, looking up things, if you start going into relation paths, it even gets more, tricky, right? So I think that's important. So I think this is a good thing to think about. And the using knowledge bases to inform embeddings, what this is focusing on is essentially helping out in the long tail instances where we don't have enough training data to inform our information about this, like entity embeddings or whatever. So one example of this is lexicon-aware learning of word embeddings. So basically the idea is we incorporate knowledge in the training objective for word embeddings, such as similar words should be in close places in the space. I'm sorry, I think I lost the equation that I had here. But basically, if I remember correctly, what they did was they took the WordNet synsets, which are the sets of synonyms in WordNet, and just tried to regularize these words to be closer together during training. So this is a joint training model where you incorporate this directly in training. There's also models where you pre-train the word embeddings, not thinking about knowledge whatsoever, but fit the embeddings to existing lexicons. So the idea is that basically you do a linear transform of the embeddings or something like this to ensure that particular relations hold well between them. And the good thing about this is if you have your fast text embeddings or whatever embeddings online, you can just go and download them and apply this fast retrofitting procedure to make it work. So they had a double objective of making the transformed embeddings close to their neighbors in the knowledge graph and close to the original embeddings. So this is the first part of the objective, being close to the neighbors. And then this is the part of the objective being close to the neighbors. This is part of the objective being close to the original embeddings. You can also do kind of interesting things like forcing antonyms away from each other. So a really big problem with regular word embeddings is things like love and hate appear in very, very similar contexts. So they become close in the original word embedding space, but you can just add an objective that forces these away from each other if you have a list of antonyms. So that's another thing you can do. So getting back to the very good point that we had earlier, you can actually use this to do multi-sense embedding. So what you can do is you can create a model with a latent sense, which might be an example of a book or an example of a movie. And you essentially choose the sense by selecting the most probable sense at any point, and then optimizing word2vec based on that selected sense. So you have a probabilistic model that chooses the sense, for example, based on its similarity to the sense embedding, and then you optimize based on that sense. So yeah, I think that's all I have for now. One thing that I should note is there's lots and lots of other types of information that you can also model. There's just enough to talk about with regular relation extraction, but you can also have things like events. You can have things like schemas, which are sequences of events or scripts, which are sequence of events. You can have all kinds of other types of information that you'd like to extract. But I think a lot of the methods here can be used for all of these. So, are there any final questions about stuff I covered here? Okay, if not, I will finish up.